Hello, dear friends. Welcome to topic 8, energy production. And since we haven't covered this in class, I think I will go in depth for this rather than just a review video. This may take several videos then, and I hope you're energized. If not, I'll teach you how to produce it. Now, we need energy to do work, but where are we all getting this energy from? Well, there are two types of energy: primary and secondary. Now, primary energy is the energy that's found in nature. It's already there. You can't bring it from somewhere. It's already there. And secondary energy is the one that's processed from the primary energy. So it's more like this. Why do we process energy to make it into secondary? So that it's more versatile. Here are the different types of primary energy. We have wind, we have the sun, we use solar panels to harvest sunlight. We have water, we use dams to harvest energy from water. We have geothermal, which means that geothermal is basically the heat that is released from the center of the earth. There's biomass, which includes things like wood, animal manure, that's basically poop, if you remember. You can grow potatoes with that on Mars. We have vegetable oil and we have trash. If somebody ever tells you that you're trash, just know that you have a lot of energy inside you. And we have our fossil fuels, crude oil. We we convert that into petrol, which is a secondary energy. Natural gas, kerosene lamps back in the olden days, propane, and they're radioactive materials like uranium that can be that are found naturally on Earth. Now, the types of secondary energy includes refined oil, petroleum, and diesel, and you get that from processing crude oil and natural gas and um, electricity. The main thing you can and we have biofuels which are derived from biomass. An example includes ethanol, and these are basically the main things you need to know. I will put a link in the video description for a PowerPoint. I know this is really messy, and that would be a cleaner way to look at it. So there's that. Now, how do we know how much energy there is in a fuel, for example? And by the way, fuel is any material that can produce energy. How do we know how much energy we can extract out of them? So, for that, we use two things. There's the specific energy, and there is the energy density. Specific energy is the amount of energy in a fuel per per amount of mass, and so that's denoted by ES, and its units are joules per kilograms. Energy density is the amount of energy present per volume, per unit of volume, and that's denoted by ED with units joules per meters cubed. Now, let's do a little bit of units here. Say we divide energy density by specific energy. Now that's joules per meters cubed divided by joules per kilogram. We get joules cancel, kilograms per meters square. Aha! So now this is really just density of that fuel. Amazing, isn't it? So the energy density of a fuel and the specific energy of a fuel will give you the density of that object, of the fuel. Fantastico. Ahaha. Now, we know that there are two types of energies. We can break it down to primary and secondary. We can also break down primary energy into renewable and non-renewable. So renewable energy is the energy that's finite and limited in nature. Oh no, sorry. Oops, big mistake. Nope, that's the exact opposite.
Human after all. I'm only human after all. Don't put the blame on me.
Now renewable energy is the one that is technically infinite. This includes, I say technically infinite, I mean, nothing is actually infinite. Like, renewable energy includes the sun, for example. We all know that sun is going to explode in a few billion years. But, so, as far as we're concerned, it's technically infinite. It is replenished way faster than it is consumed. Non renewable energy, however, is finite. It's very limited. We're running out of gas right now. Once you use it, it's gone, and it's gonna take gazillion years to replace them again. So that means that it's consumed way faster than it is replenished. Examples of renewable energy include solar energy, wind energy, hydropower, and biomass, such as residues from forests and trees. The sun will be there for a long time. The wind will be there as long the sun is there. Renewable energy are basically your fossil fuels, such as petrol, coal, and natural gas, and nuclear energy is also non renewable. Now, let's say that I want to convert one energy into another. For example, there's fossil fuel, and I want electricity from fossil fuel. Let's take, I have in my inventory about 100 megajoules of fossil fuel. Unfortunately, I will not be getting 100 megajoules of electrical energy from my fossil fuel energy. That will not happen. Why? Well, let's take there's a fossil fuel plant, a plant that burns fossil fuels to produce energy. Well, it costs energy to do this conversion, and a lot of energy will be lost to the surroundings in that process. So we cannot expect in real life to convert all of our input energy into the output energy. The energy that is lost or unavailable is called degraded energy. So, lost and unavailable energy is called the degraded energy. Energy is lost. I have energy inside me, but as I am speaking, the energy inside me is released into the surroundings as heat and sound, and my hands are moving, so energy lost. Well, energy refilled. That's not quite how that works, but that's for the biology kids to worry about. Okay, let's take a fossil fuel plant. We input 100 megajoules of fossil fuel, and in the end, we only get 40 megajoules of electrical power. Recall that power is energy over time, since power is the amount of energy per unit of time. We can calculate the efficiency of this fossil fuel plant. Efficiency, which is denoted by E, equals useful power divided by input power. We got 40 megajoules of electrical power from 100 megajoules of fossil fuel power. Megajoules, megajoules, cancel, and we get 0.40. That means that the efficiency of this power plant is 40%. So, how do we represent our input energy? How do we know what's happening to our input energy when it's being converted? There are these things called Sankey diagrams. And a Sankey diagram shows you how energy flows, what's happening to the input or your starting energy. So let's take a look at this simple Sankey diagram, for example. It's pretty straightforward. When we turn on a light bulb, it uses, say, 100 joules of electrical energy. That's our input energy. Now, a light bulb produces heat, so 90 joules of it turns into heat energy. 90 joules is lost, and 10 joules, the light energy, is our output. Sorry, not our output, our useful energy. So from 100 joules, we only have 10 joules of light energy, which means its efficiency is only 10%. Now, an important thing to remember about the Sankey diagrams is that the width of the arrow, the width of the main arrow, is proportional to the amount of energy, whereas the length does not matter. The length, don't care about the length. The width is proportional to the amount of energy. More energy, bigger width. Less energy, well, all smaller right. Width. Then that is all for part one of energy production. I believe I'll do three parts, and this is it for part one. Have a wonderful day.